The previous lecture, we made a brief introduction to the transonic flow, and in this lecture, we will see the mathematical description of the transonic flow, which means we will see the governing equations to the transonic flow. Okay, so we know for 2D compressible inviscid flow, so pay attention to the three underlined words: two-dimensional, compressible, and inviscid. Okay, so we have continuity equation and the momentum equation. Since the flow is inviscid, which means we exclude the viscosity effect of the flow field. So the momentum equation is also called Euler's equation. And if just a short question, if we include the viscosity, what's the equation called? So it's called Navier-Stokes equation. Okay, so these three equations can be used to describe a 2D compressible inviscid flow. So since we consider or take into account the density change, so in the continuity equation, the density rho is within the derivative, partial derivative. Okay, so apparently the equations, the three equations on the left are nonlinear, and to solve them are not straightforward. So we need to simplify these three equations. Okay, so simplification is needed. And so before we do the simplification, we need to put the procedure onto a few conditions. So in here we call it conditions in the simplification procedure. So we have three preconditions. One is compressible flow, as actually it's and the same as in the title, 2D compressible inviscid flow. The second is inviscid. We do not take into account the viscosity of the flow field. And third is rotational. So this one is new. It's we don't see from the online word. So and also I highlighted. So what does irrotational suggest? What's a physical interpretation or suggestion of the term irrotational? And so more straightforward saying, irrotational suggests there's no flow separation. And further, if we are, since we're considering the aeronautical engineering, so if it's an aircraft wing, is considered, the surface curvature, the wing's surface curvature is small. So that's what the irrotational flow suggests. And you may wonder, if the curvature is large, what will happen? So if the curvature is very large, the flow might not be able to follow the surface curvature, and then flow separation would also take place. And so this is a physical suggestion of irrotational, this condition mean. So let's move further. Okay, now we add the irrotational into the title. Now we are looking at 2D compressible inviscid irrotational flow. Okay, and we already know 2D incompressible equation can be simplified into Laplace equation. So the Laplace equation is actually a description of the 2D incompressible flow, incompressible inviscid flow, but now we take into account the compressibility, which means the density changes. So how can we walk? How can we continue with the derivation? And in here, just a short note: phi is velocity potential. Okay, so actually we're recommended to follow a similar procedure as we derive the Laplace equation. And then we can have the following 2D full velocity potential equation. And the detailed derivation is not given here, but we will revisit the derivation in the next mini lecture. And you can see that now the notation A is highlighted with red color. And so A is the speed of sound, since we are talking about compressible flow. So and then we would concern more about the Mach number, and the Mach number is the velocity divided by a. So a is the speed of sound. And you can see this 2D full velocity potential equation for compressible 2D compressible inversely rotational flow is quite different from the Laplace equation. And again, it is nonlinear. So still, it's very complicated. Further simplification is needed. Then how can we do the further simplification? In order to carry out further simplification to the full velocity potential equation for compressible flow, we need to use a small perturbation assumption. And I am not sure whether you are familiar with this small perturbation assumption, and it's actually widely used in the flight, for example, flight dynamics analysis. Okay, so now under the small perturbation assumption, we consider the flow's mainstream is horizontal, the mean vertical speed is negligible, so the vertical speed for the free stream is 0. And then for the local velocity, it's a combination of mean velocity and the perturbation velocity. So which means the horizontal velocity is u infinity plus u prime, and the vertical velocity is u equals u prime, v prime. Okay, and since this u prime and v prime are the perturbation velocities, they are smaller than the magnitude of u infinity. So we also have u prime divided by u infinity, and v prime divided by u infinity are very small, smaller than 1, far smaller than 1. So these are the two. The left-hand side is a definition, the right-hand side is a relation we need to remember. If we reflect the perturbation velocities in the flow field. For example, we have a thin aerofoil, and at certain point in here, for example, in here, we can see the horizontal velocity is u infinity plus u prime, and the vertical velocity is v equals v prime, and the red vector is a resultant velocity. So because it's, for example, this point is at the after portion of the aerofoil, so if the flow is irrotational, and the vector should point, namely the red vector should point towards the down right direction. It's actually what happens like this. Okay. And the perturbation velocity potential. So we define the perturbation velocity, and then similarly, based on the perturbation velocity, we can define the perturbation velocity potential. And for the perturbation velocity potential is phi prime. So phi, the velocity potential equals u infinity times x plus phi prime. And this is derived through the first equation. So we can treat u as partial phi partial x, and u prime is partial phi prime over partial x. And then we do the integration, and we'll have this relation phi equals u infinity times x plus pi prime. And because the perturbation velocity potential's definition is similar as the full velocity potential, so we have u prime equals the partial phi prime divided by partial x. V prime can be partial phi prime divided by y, divided by partial y. So that's the relation. Okay, so let's see how can we utilize these relations to do the simplification. Okay, so what we can do is just plug in the velocity, perturbation velocity potential into the governing equation. We will have this part. The left-hand side of the simplified equation is quite neat. And the first one, partial phi prime, partial x, or it is a signal derivative of partial phi, partial x. So the coefficient is 1 minus m infinity square, and the second is just 1. But on the other hand, on the right-hand side, it's a bit complicated, complex. So but if we address each term progressively, we will see a better solution. So we start with the second hand one, middle one, and we know partial v prime partial y is negligible. Why is that? So consider the plot in the previous slide, and we can see, so partial v prime partial y is the velocity change, vertical velocity, local vertical velocity change along the vertical direction. So for mostly the subsonic, transonic, and even supersonic flow, this is true. Partial v prime partial y is negligible. And now let's see the second. The second is partial u prime partial y and a partial v prime partial x. And apparently, since we're just looking at the free stream inviscid and we don't take into account the boundary layer, then partial v prime partial y is also negligible because we don't have velocity gradient along the vertical axis. And also for pi v prime partial x, so there's a minimum change of the streamwise or normal velocity component. Okay, so now let's move to the most important one, that first term. Regarding the first term on the right hand side, the streamwise velocity change is no longer negligible. So why is no longer negligible? As soon as the shockwave appears. Why on the right hand side the first term is not negligible? This is because, let's see, partial u prime partial x, I highlighted these words. For the rest in the bracket, we have u prime, u infinity, so it has a magnitude of far less than 1. And it's the same for u prime divided by u prime infinity. It's also a very small number. U prime v prime, u prime divided by v is also far smaller. Smaller terms add two or three smaller terms add together, they are still smaller terms. But if we look at the right hand side, partial v prime partial x, and this suggests a streamwise velocity variation or streamwise velocity change. So can we automatically say this one, partial u prime partial x, is automatically negligible? The answer is no, we can't. Why? So it is okay for subsonic flow or supersonic flow, but this is not true for the transonic flow. And if we see the transonic flow, we can see the a shockwave or normal shockwave is established over an aerofoil, and so the flow is from left to right. U1 is the velocity upstream the shockwave, and U2 is the velocity downstream the shockwave. And from the aerodynamics, fundamental of aerodynamics module last year, and you will know U2 is larger than U1. So in this case, if U2 larger than U1, which suggests there is a horizontal gradient, big horizontal gradient in streamwise velocity, so we can't automatically say the first term can be eliminated for the transonic analysis. Okay. And so we have this governing equation for 2D compressible and irrotational. And also we use the small disturbance assumption. So this equation is definitely nonlinear. We need to use a numerical method to solve it. But on the right hand side, we know why it can't be eliminated. So you can see, and to address the transonic flow, we need to study an equation like this, which is quite complicated. And that's also why this phenomenon is so interesting. Okay, so this is a part of the lecture 2.1.